Hello, everyone. Welcome to the Frontier Seminar. My name is Javier Garcia. I'm a NASA Goddard, and together with Caroline Kierans and Drew Miles, we are organizing the Frontier Seminars currently, which are hosted by the executive committee of the HEP. As a reminder, this is an initiative that started back during the lockdown because of the pandemic, as a way to allow young researchers to promote their research, and it's been very successful. So we have continued doing so, and the cadence is typically around every 3 months. We ask for nominations, either self-nominations or to nominate somebody for giving these talks, and we work really hard to try to select the ones that we think are most deserving. But it's always hard because most of the nominations we have are very, very good. So we ask you to please continue joining, please continue this initiative, because we believe it's very important. So today we have 3 speakers, as we usually do, and I will introduce each speaker before they're allowed to talk, and each talk is going to be about 30 minutes plus questions, so we have about 20 minutes in total per speaker. First, we have Amedeo Romagnolo. He's a visitor fellow at the University of California, San Diego, and soon a postdoc fellow at the Institute of Theoretical Astrophysics of Heidelberg in Germany. He did his PhD under Chris Bolshinsky between the Nicolaus Copernicus Astronomical Center in Warsaw and the ISO in Garching. He works on theoretical and computational improvements of stellar atmospheres and winds of massive stars, and the consequent formation of stellar mass black holes and gravitational wave sources. His research aims to constrain uncertainties in stellar physics and population synthesis models for current and future gravitational wave observatories like the Einstein telescope. As a member of the Large Interferometer for Exoplanets Live Space Mission Collaboration, he also works on population synthesis studies of habitable exoplanets. So Amedeo, please start your presentation. Thank you for being here.
And thanks to you all to allowing to be here. So to start this talk, I believe that the best way to initiate this kind of conversations is to start with the premise that with all the due exceptions, black holes are the final aftermath of the evolution of the most massive stars that we can currently observe in our universe. But the evolution of these massive stars that can produce observable black holes is still affected by many uncertainties that can lead the evolution of a star through very different pathways. And some of the major factors affecting the evolution of these stars are how efficiently they mix in their interiors, and also how much mass they are losing due to their stellar winds. Stellar winds are extremely important because they determine how much mass and angular momentum has been conserved in a star as opposed to what has been ejected. So if I have stronger stellar winds, I'm ejecting more mass and angular momentum, and therefore my star will collapse into a lower mass, slowly spinning black hole. On the other hand, if I have weaker stellar winds, what will happen is that more angular momentum and more mass will be conserved, and therefore I will have a fastly rotating, more massive black hole at core collapse. And to introduce you all to this wonderful environment and research area of stellar winds, I would like to start with the 3 main branches of stellar winds that can affect the mass loss history of our stars. Starting from left to right, we have optically thin winds that are typical of OB-type stars, and they are the stellar winds that last the longest. Usually, these optically thin winds can last for the whole main sequence of a star, if not even more, but they are also the weakest ones. So even if they last for a long period of time, overall, these stellar winds will contribute the least to the overall mass loss of our star. On the other hand, we have the optically thick winds that are more typical instead of Wolf-Rayet stars. these optically thick winds are extremely dense and extremely fast, and they lead to the strongest ejection of matter throughout the whole stellar lifetimes, even though they last for relatively short periods of time. And this is because mass loss rates from optically thick winds are orders of magnitude stronger than optically thin winds. And then we have a case somewhere in between in terms of mass loss rates, which is the dust-driven winds phase, where we have a post-main sequence star that has expanded enough to become a yellow red supergiant and has the outer layers that are cool enough to develop dust grains. And these dust grains are extremely opaque, and with the help of the radiation pressure coming from the star, they lead to considerably high mass loss rates. But of course, this understanding is extremely simplistic because we had plenty of different theoretical and observational measures of how much a star should lose in terms of mass in each of these stages. And each of these mass loss rates estimates can considerably vary throughout the whole parameter space, both as a function of effective temperature and luminosity. And you can see here that each of these lines represent a different mass loss model for massive stars. And these lines can lead to mass loss rates that diverge by orders of magnitude. And this is the same thing not only for optically thin winds, but also for the optically thick case, and as well as the dust-driven winds phase, where we have a considerably strong dependency on effective temperature and luminosity for our stars, but models diverge in how they should be prescribed in our evolutionary codes. And this is a considerable problem because this leads to a jungle of different evolutionary studies where each of these studies prescribe stellar winds in a different way. And this table that I'm showing here, it's just a small piece of a wide array of different studies that define stellar winds differently. And more in particular, I highlighted in yellow here what are known as the Dutch wind models, which are usually the ones that have been used for decades in our evolutionary codes to simulate the mass loss rates of massive stars. And I hope that within the end of this talk, I can prove to you that they are not as accurate as we thought, and we should drop them for more accurate prescriptions of stellar winds. But in general, the overall problem here is that uncertainties are many, and no code actually reached a point at which many different stellar winds models have been tested within the same stellar evolutionary framework. And this is what we are currently doing in this very moment, where we are developing what we are calling the Stellar Wind Atlas for black hole formation and solar metallicity, where we analyze a wide array of different stellar masses that can lead to the formation of a stellar mass black hole and solar metallicity within a common stellar evolutionary framework. So for each of our array of simulations, we are changing not only the mass loss prescriptions for the major winds phases, but also other factors such as how a rotation couples with stellar structure and stellar winds, and also when an optically thin wind star should transition to dust-driven winds or optically thick winds. And in particular, optically thick winds, how they start transition to the Wolf-Rayet phase is still a subject of debate, because canonically speaking, with the Dutch wind models that I told you about before, the transition to the Wolf-Rayet phase that is characterized by very high mass loss rates was set as a function of surface hydrogen abundances, because in previous decades, we thought that only stars with low hydrogen abundances can become Wolf-Rayet stars. But now that we have observed hydrogen-rich Wolf-Rayet stars, this paradigm has to change. And therefore, new ways have been developed to actually prescribe the transition to the Wolf-Rayet phase, such as the proximity of the surface to its orbital limit, or the optical depth of the stellar atmosphere itself. And within this whole study, we have developed a more deterministic understanding on how changing a specific factor in our stellar winds modeling can lead to different results in terms of which black hole we can produce from a specific star. And this is roughly summarized in this plot over here, where you can see the black hole mass, or it is a function of the initial mass of the progenitor star, with this left plot being simply a zoomed version of this dashed region over here. And each line that you can see here represents a different model for stellar winds throughout the whole initial mass range. And there are many interesting things to notice from this plot. So first and foremost, we know that every model that applies the Dutch wind prescriptions seem to prescribe the formation of an early black hole mass peak. That is mainly due to the fact that they are considerably overestimating the mass loss rates beyond a certain initial mass. But this is probably the least noticeable information about the whole, from this whole plot, because there are other interesting things to notice, in particular here in this region. The only way that I can form a black hole from the evolution of isolated stars' solar metallicity is by considerably underestimating the amount of mass that has been lost during the Wolf-Rayet phase. So this region is forbidden from isolated stellar evolution and can only be reached through other channels. So if we observed a black hole of this mass within solar metallicity environments, this will mean that this black hole was not born from the isolated evolution of a star. So maybe it came from a stellar merger or mass transfer events, or many other evolutionary channels that are beyond the isolated case. Also, another interesting result comes from this peak over here, which is another early black hole mass peak around 30 to 60 solar masses at the zero-age main sequence. And this peak comes from the collapse of red and yellow supergiants into black holes. Because this is extremely important, because this means that a star is collapsing not only with the entirety of its core mass, but also with at least part of its envelope mass, and therefore producing very high black hole masses. And this can also be seen in more detail in this HR diagram here, where I'm showing the evolution of a 40 solar mass star, again, still solar metallicity, when I vary the effective temperature below which strong dust-driven winds are initiated. So from 4 kilokelvins until 10 kilokelvins. And what we see in our plots is that if we don't give enough space for dust-driven winds to actually eject enough mass, this will lead us for stars to die in these positions here as either yellow red supergiants and collapse in considerably massive black holes. On the other hand, if we enable dust-driven mass loss earlier in the evolution of a star, the star will have more time to eject its hydrogen-rich envelope. And what will happen is that the whole envelope will be expelled and the star will evolve leftwards towards the Wolf-Rayet phase, and therefore producing considerably less massive black holes at core collapse. But this is also an interesting point that we are seeing, which is that if a star gets to the Wolf-Rayet phase, you can see that all the tracks seem to converge roughly, besides this one, but roughly to the same effective temperature and luminosities, and also to the same black hole masses, which seems considerably weird, considering that we are considerably altering the amount of time that a star spends during the dust-driven phase. And this is also more noticeable if we go back to this plot over here. Because look at all these lines here for very massive stars. All these lines, technically, they don't converge specifically at the same black hole mass, but qualitatively, they have roughly the same behavior, and they converge within a not wide regime of black hole masses. And the same thing can be said about these two lines over here. And what is in common among all these lines is only how we prescribe the mass loss from Wolf-Rayet winds. So in general, what seems to be the case is that the final mass of our black holes is only dominated by how we prescribe Wolf-Rayet winds and nothing else. And this can be better represented by this diagram over here, where I'm splitting the evolution of stars in different cases, depending on their initial masses. And we have the formation of two different evolutionary channels. The first being the supergiant pathway, where a star becomes supergiant and stays a supergiant until the end of its evolution and collapses into a higher mass black hole. While on the other hand, we have the Wolf-Rayet pathway here, where instead, if a star manages to get to the Wolf-Rayet phase, it always roughly converges to the same lower black hole mass. And this is due to a specific factor, which is that Wolf-Rayet winds are considerably stronger than any other winds, be it optically thin or Dutch-driven winds. So this means that Wolf-Rayet winds are so strong that are completely erasing the previous evolution of a star. And therefore, Wolf-Rayet winds can be tested even almost uniquely on the black hole masses that we can observe. But also, I'm not saying that the black hole masses are the only way that we can constrain stellar winds. There are also other ways. And another way that I developed and in my stellar wind atlas is looking at stellar populations in the Milky Way specifically. And more specifically, to the population of OB and Wolf-Rayet stars at the same time. As you can see here in this HR diagram, and in the top middle, you can see that OB stars tend to disappear past a certain luminosity threshold. And this is because OB stars that are the blue dots here, beyond a certain point, they reach so high mass loss rates that they will already be born as Wolf-Rayet stars in the first place. So past a certain luminosity threshold, every star, at least as our metallicity, should be born as a Wolf-Rayet star. And this can be a nice way to test our stellar evolution models, because we could have stellar evolution models that overpredict the amount of superluminous OB stars, like the ones that you can see here. And of course, they're wrong because they are too optimistic for when an OB star can actually be detected. And among them, as you can see, there are also the Dutch wind models. So if someone will ask you why the canonical stellar winds models don't work, the pitch is simply that they overestimate mass loss and the formation of superluminous OB stars. On the other hand, we can also have the opposite case, which is that stellar wind models are too optimistic in the formation of Wolf-Rayet stars, and they don't allow for the formation of OB stars, where at least we are observing them. And this is an effect.
Sorry, Amedeo,
Yeah.
we're getting over the time, so
Yes,
if you can
I'm done.
wrap up. Yeah, okay.
I'm done. So long story short, this is a great way to test which stellar wind models can actually be excluded from observations and theory. And with this, I leave you with my conclusions.
Perfect. Thank you so much. Sorry for the interruption. I wasn't
Don't
sure
worry
how
at
long
all.
you had.
No,
Right.
yeah.
Very interesting talk, by the way.
Thank you.
Please, any questions for Amedeo? I have a few. Well, people
Sure.
feel more courage to ask. I think the biggest one I have is if you can say a bit more about Cygnus X1. You had it in your
Yes.
slide, and Cygnus X1 is always being a little bit of a confrontational point because with X-rays we measure the spin of the black hole is always at maximum, and I have heard more than once people that work in evolution models saying that that's very hard to explain based on things that I do not understand. Do you have any thoughts about it?
Yes. So the fact of the high spin is probably the huge bottleneck in evolutionary studies for concerning Cygnus X1. Even because, I mean, the accretion can explain the fact that the black hole is highly spinning, because again, if we are accreting enough mass, it means that the spin is supposed to increase. For sure, that spin is not primordial. This is something that we should have clear in our mind, and that's because, again, being stellar metallicity means that the winds are strong enough to eject the whole angular momentum before core collapse. But the other point is that the question is, can Cygnus X1 be explained with the quasi-isolated evolution of a star in solar metallicity within this binary? The answer is probably yes. As you can see, at least within this region, all the models predict the formation of a black hole such as Cygnus X1, and being in this region of the Itzam's mass regime means that roughly we are respecting also the IMF, and therefore we are more likely to form this kind of star. This kind of black hole. So yeah, it's a long shot to say that any model can explain Cygnus X1, but its existence is not against the quasi-isolated evolution of two stars within the same binary.
That's it. Thank you. Well, I'll be interested to talk more to you about that.
Yeah, sure.
I see Lini has her hand raised. Go ahead.
Yeah, so I am very confused by one of your earlier plots where you show like the temperature of the star and like the mass of the final black hole. This one.
Oh,
The one,
look,
wait, not this
temperature?
one after.
Hold on.
Or
The black hole of the okay, this one you mean.
yeah, like so
Okay.
I'm a bit confused
Yeah,
because
sure.
like I don't know, are you like you're basically like I don't know, because it sees like the stars with like in the chart on the right, it looks like the stars with the higher temperature are the ones creating bigger black holes, but you've said it's the other way around.
So this one is the one at the lowest temperature, which is at the 4 kilokelvin.
Okay, I'm
And
sorry.
no worry.
I'm dumb. I'm dumb. Like you
No
colored
worry.
it in reverse of how the black body colors would be. That confused me. I'm sorry.
No, don't worry. I mean, probably, my color scale was also confusing because of like the different arrows that were started. This color and this color are very similar. But yeah, so the ones that initiate the striven winds earlier, so at higher effective temperatures, are ejecting more mass and are creating less massive black holes.
Okay, sorry.
Great.
Don't worry.
I'm afraid we need to move on, but any other questions, please feel free to write it in the chat, and Amedeo can get to those by writing them.
Absolutely.
Thank you again, Amedeo. So we're now going to move to the next speaker, who is Julie Malewicz. She's a PhD candidate at Georgia Tech Center for Relativistic Astrophysics, where she works with Tamara Bogdanovich and David Valentine on the X-ray properties of supermassive black hole binaries. She also works with the science teams of LIFA, Nanograv, Axis, and New Athena. Julie, welcome. Share your slides and start your presentation, please.
Yeah, first of all, I wanted to thank the organizers for giving me the opportunity to talk about my work here. Let me see. Okay, can you see the screen? Okay, beautiful.
Yes.
Yeah, so my interest is in using X-ray reflection spectroscopy to identify and characterize supermassive black hole binaries. And so for the most part, I'll be drawing from this paper that we published earlier this year. So if you're curious, there's more in there. But yeah, so I might be biased, but I do think that supermassive black hole binaries are going to be the next frontier in multi-messenger astronomy. As loud emitters of low-frequency gravitational waves, they will be heard by both LISA and the pulsar timing arrays in the very near future. LISA being, the laser interferometer space antenna, which will launch in the mid-2030s, contemporary with ESA's flagship X-ray telescope, New Athena. So, this is, I hope, timely work. I'm going to be making some assumptions about what this audience is familiar with, so I'll be brief here, but I can also just go back if people have questions. But in summary, where do the X-rays actually come from? In the lamppost model, the disk is illuminated by the corona. Light bending will strongly focus the coronal rays onto the innermost regions. It is reprocessed there by the cold accretion disk, absorbed, re-emitted, and or scattered, which gives the spectrum its reflection features. Here, for example, this forest of spectral lines roughly from 0.1 to 2 keV. And here, the ubiquitous iron K-alpha line, usually around 6.4 keV, both of which are very strongly impacted by relativistic affects the relativistic space-time that they, originate from. So they get blurred, broadened, shifted, all of that. Another big thing is that spin of the black hole will determine just how close to the black hole the inner edge of the disk is able to get. And so it's the extent of the most severe of those relativistic effects. But if there's something I want to emphasize, because it is relevant for binaries, is the importance of ionization throughout the disk. So ionization is proportional to the illuminating hard X-ray flux from the corona. It will decrease with radius, and it is central to determining how the gas in the disk is able to interact with that illuminating flux. Are atoms too ionized to absorb anything at all? What kind of species of ions is dominant, what kind of electron shell vacancies you got, how dominant is scattering by free electrons, et cetera, et cetera. So it very, strongly affects reflection features. So any binary model is going to have to treat mass accretion and ionization very carefully, which is what we aimed for. And now I think is a good time to, zoom out and go over the typical binary geometry. So what we have is two black holes orbiting a common center of mass, which we model as roughly circular for simplicity. So this motion will clear a cavity, a low density cavity where there's little to no gas. Each black hole will retain its own so-called mini disk, which is fed by the circumbinary disk, which extends much further than this. It's just I didn't want to draw all of it. They feed the mini disks through those accretion streams. And so the main binary effects that are going to be that concern the production of the X-rays are first going to be Doppler modulations from the orbital motion of the two black holes. So their velocities can reach, a few percent of the speed of light. So periodic Doppler shifts and boosts in opposite directions for, either spectrum. The second thing is that in unequal mass binaries, the secondary, which is the less massive one, black hole will orbit further out from just the center, closer to the inner edge of the circumbinary disk. It accretes more rapidly from that privileged position, which can put the two mini disks in wildly different ionization and accretion regimes. And finally, an obvious one, I guess, is that the mini disks do get truncated much closer at their outer edge, much closer than a single black hole would be. But to build some intuition around this idea of accretion inversion, we took the mass ratio of the two binaries and the total mass accretion rate onto the binary as a whole, and calculated the fraction of that gas that is expected to accrete onto either the primary to the left or the secondary on the right. And so the numbers aren't as important as the first big takeaway being that for a mass ratio, especially around 0.2 where it peaks, the two black holes will be in very different accretion regimes. You see that in black, it is just very inefficient accretion, sub 1% of Eddington, whereas the secondary in that same region is going to be accreting way past the Eddington limit. So that's where just any alpha disk prescription assumption just breaks down. And this translates directly to ionization. Oh yeah, to ionization, which you can think of the peak ionization as an overall scaling factor for the ionization gradient throughout the disk. So it, again, just affects the disk's ability to reprocess that radiation. And yeah, so we can take a look at how this translates to like actual spectral morphology. So all of the little bubbles that have their little letters are going to correspond to spectra here. And at first glance, we recognize the broad iron line, the soft X-ray forest of lines to the left, blurred by relativistic effects, and the Compton hump to the right. We see that in, half the cases here that we just like sampled through, that we looked at, the primary and the secondary dominate in different frequency bands. And partly because of that, the composite iron line can start taking on this just abnormally stilted, like extra horned morphology. So the next step is actually just to take a look at one of those iron lines closer and wonder what the other effect that is relevant to binaries, i.e. the orbital Doppler kind of affects that morphology. So we're looking at this binary at throughout its orbit at 3 different inclination angles, from lowest to highest line of sight motion throughout the orbit. So in all 3 cases, we can see both constituent spectra. So in blue, green, that's the secondary, which is brighter. We can see that the both constituent spectra oscillate around the binary rest frame, with the brighter secondary orbiting faster because it's further out from the center of mass. There's also an obvious give and take going on with the inclination, where a lower inclination will mean sharper features and a clear dual peak, here, for example, but less pronounced orbital Doppler. So, and vice versa. And this is all assuming, coplanar mini disks and binary orbital plane. So all in all, variability is, promising as a tool for detection and measurements. But since we're personally interested in sources that are detectable in gravitational waves, the variability for that, the time frame for that variability is critical. So if you take a PTA, a pulsar timing array type binary, which tend to be heavier, 10 to the 9 solar masses, with an orbital period on the order of a year, we can just probe the binary at different, get snapshots at different points in its orbital evolution. Whereas for a LISA type binary, which tend to be lighter, less massive, the orbital period is on the same order as what a typical exposure time would be. So that variability is going to get washed out mostly. So in practical terms, how do you best leverage our, X-ray telescopes to actually find a binary? So that's the question we're trying to answer in this section. This section is a lot more extensive in the paper, but I will be brief here. I'll use New Athena as an example, but if you're curious about the other ones, they're in the papers, or I can answer questions. Athena and Axis are both sensitive from about 0.2 to 12 keV, with Athena bringing the XIFU to the table, and so just exquisite spectral resolution and collecting area in the soft band. And so, yeah, the question becomes, how can you tell you're actually looking at a binary? And we found that the simplest way to answer that question is simply you begin by faking observations of the binary model spectra. And then we force fit those with a single black hole model to identify points of friction, just where it breaks, where it doesn't fit, where there's, friction. And we're looking for roughly three things, which I will illustrate next. The first one just being simply a bad statistical fit. Reduced chi-squared, especially more than 2. Atypical, unconstrained, or variable fit values. And residuals in some part of the spectrum that is not that cannot be explained by just typical AGN phenomenology. And so this is going to be the example using Neo-Athena, its X-ICE view. What we're looking at is the single black hole fit on top of the binary count rates, and the residuals, which is just the difference between the two, are at the bottom. And we find that for all telescopes, not just Athena, but at a redshift of 0.1, you just get a bad fit. The single black hole model is just not a good fit for the binary observation. But the useful information, I think, is where the residuals are, which they tend to cluster in the soft part of the spectrum, which is particularly sensitive to changes in ionization. And so a composite binary spectrum it combines features from two mini disks in potentially very different ionization states, especially when the mass ratio Q is much less than 1, or even just a little bit. Because even here, where the mass ratio is 0.9, so close to 1, the orbital Doppler just desyncs the lines from one another, just resulting in a confusing spectrum for the software to fit. And compared to those residuals, the iron line looks almost unremarkable in comparison, but we note that, for example, at redshift 1, the spin is just completely unconstrained, which may be indicative of an abnormal iron K profile, which is usually what is used to constrain the spin. And for the next slide, I think I'll skip over the details and just keep the takeaways. But this one, we're just looking at variability throughout the orbit. So we're just sampling it at 3 extremal points in the orbit, where the Doppler is either maximal or 0. And even if the residuals around the iron line look slightly unremarkable, with very high quality data like this, the fitting process is quite sensitive to even small variations in the profile. And so the best fit spin values kind of reflect that. They are just, unconstrained, variable. The WFI just even thinks we're looking at a retrograde black hole, and then you check back in 2 months later and it thinks it's fully prograde. And then I think, I'm going to be switching gears a little to talk about results we haven't published yet. And so it's
Julie, we're kind of over the time of getting there. So if you can just be very brief, one more minute.
Okay, yeah, for sure. We can get some inkling of binary parameters from very simple measurements from the spectrum. But with the peak, we can get the inclination, and by looking at how the centroid shifts, we can get mass ratio and orbital phase. And I can just leave my takeaways on the screen.
Perfect. Thank you so much. Also very interesting talk. I see Lini has her hand set for a question now from this previous one, Lini. You have any question? Yep.
I have a question, and actually I have I have 3 questions. Okay, first one, what are the prospects of detecting these weird iron line shapes with CRISM?
Oh, I'm not as familiar. I mean, I think it's a possibility. Yeah, I'm not as familiar with Chrism, I'll be honest.
Okay, second question. Are you going to be able to repeat this with like a different geometry for the corona, given that XP has disfavored the lamppost model?
Yeah, I mean it is like we're using Relxil, which I think just implemented the ring-like geometry for the corona in the latest version. So we can, yeah, definitely alter that. I think that uh a lot of our results aren't as dependent on just the exact geometry of the corona because it's more uh, larger scale effects that
Mhm.
and there's no one size fits all. It's just um, yeah. So like
Okay, and
we can
then
definitely do that.
my last question is, what did you use to make all your illustrations?
Um, ooh, I think we get Photoshop for free at Georgia Tech.
Okay.
So I've yeah, this and just PowerPoint.
Mhm. Okay.
Okay, maybe we have time for one more quick question for Julie. Maybe, okay, Dan, go ahead.
Yeah, quick question. Some of your plots didn't seem like they required super high spectral resolution. I'm wondering what your simulations look like for Axis, or if you've done that before, or the other instrument on New Athena.
Yeah. Yeah, I mean we've done they're in the paper. I don't think I have them in this slide, in this slideshow specifically. Um, but yeah, and we looked at both, redshift of 0.1 and a redshift of 1, where there, since the count rate was lower, the effective spectral resolution was lower, and we still saw some, binary some effects that we could attribute to the, binarity of the source.
Great,
Great.
thanks so much.
Nice work.
Thanks, Dan. We have to move on. Thank you, Julie. And we're gonna go now with the last speaker of today is Zac Metzler. He's a six-year PhD student in the University of Maryland Physics Department and performs his research at NASA Goddard. He works on the compare prototype of Amigo, leading the anti-coincidence detector subsystem, and is interested in multi-messenger pulsar observations. He's finishing up his dissertation and will be defending next month. So I hope this is a good preparation for your defense. I'll just gonna say, as I mentioned earlier, I'm sorry. I'm gonna have to leave at the hours. I'm gonna leave Caroline to take over on the questions at the end and everything else and the wrap up. Thank you, Zac, for being here. Take it away.
All right, thank you. Can everyone hear me and see my slide?
Yep, sounds good.
Cool. Yeah, so I'll be talking to you today about irradiated pulsar planets and companions as 511 keV sources. This is work that I did with Zorawar Wadia Singh. We're both at University of Maryland and NASA Goddard. And we just recently had the paper that this is all based on accepted. It's on arXiv, but not yet published by the journal yet. A quick outline. I'll tell you some background about what we're looking at, some pulsar background, as well as some other relevant things. Then I'll talk about how we do the simulations and some initial results. I'll apply this to some known systems, talk about potential multi-messenger opportunities, and then get to the conclusions. So what we're focused on here is millisecond pulsars. Millisecond pulsars canonically form through the recycling scenario, where I have a schematic of how you arrive at many different types of pulsars on the right, but starting in the top left, you have a binary stellar system. One of them goes supernova. If the binary survives, you end up with a neutron star or a pulsar with a stellar companion. Eventually, that stellar companion will overflow its Roche lobe. You get an X-ray binary, and then eventually you're left with a millisecond pulsar system that has been recycled with some companion. Millisecond pulsars are often in binary systems, and I think it's about 80% of gamma ray millisecond pulsars have a binary. There are other alternate pathways to arrive at a millisecond pulsar in a binary. One such system is a double white dwarf merger remnant, but there are other ways as well. So like I said, there are a lot of millisecond pulsar binaries. They can have a whole host of different companions. Most of them are helium white dwarfs, but you can also have double neutron stars. You can have main sequence stars, helium or carbon oxygen white dwarfs, or this group of ultralight companions. And we don't know the exact size or composition of the companions. For a few systems, we have a minimum density where the minimum density is at least 22 or 45 grams per centimeter cubed from 2 different systems. And for context, the Earth's average density is about 10 grams per centimeter cubed. We know that there are about 532 millisecond pulsar binaries that we've observed. 426 of them are in the galactic field. But since we only see the ones whose beams are pointing at Earth, there should be many more just based on the beam geometry, and we can't see all the way through the galaxy yet for these, so there will be many more than just the 500. Like I said, we don't know what these ultralight companions are, or how massive they are, or how big they are, or what they're made of, but their composition and density may depend on the formation pathway. So I lay out 3 different examples of how you might get a companion. The first is, again, this recycling scenario. Or I started with the second one. The second is this recycling scenario where you accrete a compact X-ray binary companion's outer layers, and you're left with some dense core. This could be like the diamond planet of J17 minus 1438. This is the one that is at least 22 grams per centimeter cubed. Another one is you could have a high metallicity accretion disk, like in a double white dwarf merger. This is a possible scenario for B1257 plus 12, also known as the Lich, where we know it actually has 3 planetary mass companions. And these were actually the first exoplanets ever discovered. And the third possibility is you could have exchange interactions in a cluster. Pulsars form in star-forming regions, and so if you're in a crowded neighborhood, you can pick up a companion from another system, and that companion can have a planet. So this B162026 is a millisecond pulsar with a helium white dwarf and an about Jupiter mass planet. So again, the composition and the density may depend on the formation pathway, and what we would like to do is introduce a method to calculate or observe these 2 things. Some other observations that this is related to is the GeV and 511 galactic excesses. The 511s on the next slide. We know from Fermi-Lat observations that there is a GeV excess at the center of the galaxy, and its spectrum is similar to the millisecond pulsar spectrum. I show an image of this in the top right, and the spectrum kind of right in the middle. But it could also be dark matter, but you never want to confidently say this is dark matter, so it could also be millisecond pulsars. About 20 to 50,000 millisecond pulsars in the galactic bulge could explain this GeV excess. But you can see in the bottom, those 2 plots, the red plus signs are the Fermi resolved millisecond pulsars, and this is a whole population synthesis of where galactic millisecond pulsars may be, and Fermi cannot see deep enough to really start observing in the bulge. So if millisecond pulsars are a possible candidate for the GeV excess, could they also contribute to the 511 excess? We know through integral observations that there's also a 511 excess with 4 different components. We know that there will be more than just millisecond pulsars in this. There will also be supernova remnants and X-ray binary accretion disks and other things, but millisecond pulsars may also contribute. At least that's what we are showing here, or we will show. The narrow Gaussian has a similar shape to the GeV excess. This is one of the 4 components of the 511 excess. And other studies have said that low mass X-ray binary accretion disks could be a source of these positrons. Well, if there are low mass X-ray binaries that are accreting, then there should also be millisecond pulsars through the recycling scenario. So all of this is setting up why this is interesting, relevant work. And the work is simulating what happens when you have the pulsed GeV gamma ray emission from a pulsar on its companion. We're looking at 12 different companion models, and we're using a power law with exponential cutoff gamma ray spectrum. This is representative of the measured millisecond pulsar spectra from the Fermi-Lat third pulsar catalog. We're assuming that the companions are filling their Roche lobe, because if it's compact, it'll be brighter. And since millisecond pulsars form through the recycling scenario, they should be somewhat close to having filled that Roche lobe. I show a schematic in the center of your screen where the neutron star is emitting electrons, positrons, and high energy gamma rays at the companion. They will shower in the surface of the companion. Some of the positrons in the shower will produce or annihilate with the electrons in the companion. Those will produce 2 511 keV photons. If this occurs near the surface, then they can escape and be observed here. I do this all with a Monte Carlo simulation using Megalib's Cosima Cosmic Simulator tool, which runs on Geant 4. And one of the event displays of the particle shower is shown on the right, where we're tracking all of the different particle motions as well as the escapes. Some of the results here, you don't need to memorize the whole table. There won't be a quiz. But just some key takeaways are the white dwarfs and the large main sequence stars are the brightest, although bright is kind of funny because these are very faint lines. We also see that the high Z planets, I should have mentioned, we did 5 different planet models with different compositions. The high Z planets are brighter than the low Z planets. And the results are scalable with companion size, pulsar luminosity, and the orbit separation, as long as you're maintaining that the mean free path in the crust is much less than the companion radius. Now, how might we suppose we can observe the lines, how might we use that to learn about the companion? Well, the first thing that we can do is we can constrain the inclination. We can do this 2 ways. The first is we can look at the flux variation throughout the orbit. On the bottom, on the left-hand side, I show the backsplash 511 keV flux from the iron planet model, where the yellow is where the emission is brightest, the blue is where the emission is dimmest. The way that you can read this is, suppose you are the pulsar and you're looking at the companion. So right in the middle would be the photons that are coming right back at you. And then as you go out from the center of the eye, that is leaving getting higher theta away from you. So on the very edges, that's emission that will be behind the companion from the perspective of the pulsar. If you are at different inclinations, like if you're right in the orbital plane, you'll have this double peak feature as you go over the two sides of the eye. But if you're, say, like 60 degrees out of the plane, you'll have only a single peak. And if you're 90 degrees out of the plane, you should have near constant emission. You can also do this with the Doppler shift of the line because this is a compact binary. And so on the part of the orbit where the planet is coming at you, you'll have it Doppler shifted right or higher energy, and in the other half of the orbit, you'll be Doppler shifted lower. So at 0 degrees inclination, which is face on, there should not be much Doppler shifting, but if you're in the orbital plane, you'll have maximal, and you can have up to plus or minus a keV. Yeah, you can also constrain the ultralight companion's composition. Like I mentioned earlier, the high Z planets are brighter, but you also have this double peak feature changing with planet composition. So in the bottom right-hand corner, this is in the orbital plane what the normalized line flux at 511 keV. And you can see for the iron planet model, this is the higher Z, you have a shallower double peak. But if you have a helium planet, so low Z, you have a really deep peak. And so, yeah. And then I also plot this more as a trend on the top, but it's saying essentially the same thing. We can also consider known millisecond pulsar binaries. These are selected circular millisecond pulsar binaries with defined companion type and EDOT from the ATNF pulsar catalog. And here we see that the Black Widow and Redback systems are brightest. These are two very compact pulsar classes of pulsar binary systems. We also see that the carbon white dwarfs are the dimmest. And then am I running out of time?
Yeah, I'm going to interrupt, Zac, if you could quickly wrap up.
Yeah, so we're missing a lot of the ultra compact binaries. Here's a spectrum. One way that, so we know that we're missing a lot of the ultra compact binaries because radio pulsar surveys are inherently biased against these due to Doppler smearing. These should emit in the LISA observable range. The ultralight ones maybe not, but if you have a compact helium white dwarf millisecond pulsar binary, these will have SNR hundreds with LISA. And so if we simulate one of those, we have plus or minus 1.6 keV Doppler shifting and a much more prominent line here. Some population synthesis found that there should be about 7,000 of these systems in the galaxy, and the far field approximation that we used earlier in the simulation may no longer be appropriate because being so close together, you might need to be a little more careful with that, and that may make the peak flux even brighter. So sorry for going over. Here are some conclusions. Compact millisecond pulsar binaries produce 511 keV photons. We showed that for the first time. The orbital dependence of the 511 keV flux constrains the inclination and companion composition, allowing for exoplanet or gamma ray exoplanet characterization. Also unmentioned, but there are 4 other components of the initial irradiation in addition to the GeV gamma rays that we neglected. So the line is likely brighter than what we estimated. And a joint LISA MEV search could target brighter ultra compact binaries that radio surveys cannot. Thank you.
Thank you, Zac. And sorry, you started late, I acknowledge, so we let you go a couple minutes extra. So thank you, Zac. If anyone has any questions, please raise your hand. I do see one from Sarah in the chat. Feel free to unmute yourself, Sarah. I'll give you a couple seconds, and if you don't, I can just read it for you.
Yeah, sure. I can unmute. Hi, everyone. Sada Hasnain. I'm based at EPL, so also in Maryland, not too far away. But I thought this work was really cool. My background's in pulsar astrophysics and the wonderful world of research software engineering. So I'm, sitting here wondering, are there tools that you wish existed to model the dynamics of binary pulsars or multi-body pulsars? Like if you had a research wish list, if you could just go on GitHub and find that one thing that someone else already made to make your work easier. I'm curious what that might look like.
Yeah, so one of the things that and one of the reasons why we kind of neglect some of these four other components are there are not the current tools to model showers in crusts at, say, TeV energies are slow. And so I think that would be, this is kind of dodging your question on like, binary dynamics and things. But I think even just having like faster Monte Carlo simulations
Yeah,
for
that makes a lot of sense. So it's more of a compute processing as opposed to like a level of fidelity.
Yeah. So in the paper, we go and justify why we're neglecting these four. And in order to do it, so there, a lot of pulsar systems may have TeV halos, which could enhance this kind of emission that peaks around 10 TeV or something like thereabouts. But in order to get like a statistically significant amount of results in our simulation, we ended up projecting over like 2 orders of magnitude or something, just because simulating a 10 TeV shower in this was taking like hours per photon.
Okay, and we have one more question from Lenny.
Okay, so it seems that you seem to be indicating that you think there is a large concentration of pulsars in the galactic center. And I find that interesting because I've also seen papers where they claim there is a lack of pulsars towards the galactic center. Although they explain this using primordial black holes, so I don't know how seriously I should have taken that paper.
Yeah, I don't think that we know how many pulsars are in the galactic center, because Fermi can't probe that deep, and the radio is kind of obscured by dust. And so this is kind of one of the more open questions, which is why, like, so some people have done population syntheses that find that there may be up to 100,000. Other people kind of scoff at this. I think that there's at least an order of magnitude uncertainty on the actual number, and no one really knows.
Okay, thank you. In the interest of time, we're going to wrap up. So I want to give a big thank you to our 3 speakers again, Zac, Julie, and Amedeo. Really appreciate the fantastic work that you guys are talking about today. I do want to highlight, we will probably have our next Frontier Seminar Series in late November or early December. We hope to see many of you at the HEAD meeting coming up in October. And everyone, enjoy your weekend. I hope you have